VHDL also has support for some user-defined types. Examples of these are the array and the enumerated data type. The array allows you to create a two-dimensional data type for storing values. And I want to put data type in bold because you're creating a data type, not an actual structure. Then, after you create the data type, you have to create a constant or a signal or a variable of that type. We use arrays to create memories and also to store simulation vectors. So here is what the array type declaration looks like. You use the keyword type followed by the array type name. Again, this is the data type name. Is array, those are both keywords, followed by an integer range which specifies the depth of your array. After that is the keyword of, and then the data type. Basically, what type or what information can be stored in each address of your array. Here's a snippet of an architecture that is declaring an array. So I have the keyword type, and the name of the type is mem, is an array. The depth of the array is 0 to 63, so there's 64 address locations in this array. The array is made up of standard logic vectors, each 8 bits wide. So essentially I created a new data type named mem, which has 64 locations, each storing 8 standard logic values. Then I need to create a signal or a constant or variable type that is of that data type. So in this case I have a signal called mem underscore 64 by 8 underscore a, which is of type mem, and another signal called mem underscore 64 by 8 underscore b, which is also of type mem. This creates two 64 by 8-bit arrays to use in the design. Then down in the design, to access address locations within the array, I use integer values in parentheses. So in the first line in the architecture body, I'm accessing address location 12 within mem 64 by 8a and assigning it the hex value of A4. In the second line, I'm accessing address location 50 within the mem 64 by 8b and assigning it F0. And lastly, the enumerated data type allows you to create your own data type, name, and values. Like the array data type, you are creating a brand new data type. So you must, after creating it, you must also create a constant, a signal, or a variable that is of that type. We use enumerated data types in VHDL in state machines. They can be synthesized into state machines, and we also use it just to make code more readable sometimes. The declaration for an enumerated data type also uses the keyword type followed by your data type name. So that's the name that you want to create, that you want to use to define your brand new data type. Is, and then in parentheses are the data type items or values. So these are the names of the values of your data type, each separated by commas. So looking at the code snippet at the bottom, we have a brand new type called enum, is, and the values of it are idle, fill, heat W, wash, and drain. So I have a brand new data type called enum that has 5 different values. Then I need to declare a signal that is of type enum. So this signal is called dishwasher underscore state, and it is of type enum. Then down in the code, I can actually assign the values, the 5 values, to my signal. So down here I have drain underscore LED gets the value of 1 when dishwasher state equals drain, else drain LED is 0. So again, I've defined a brand new data type, and the synthesis tools, simulation tools understand, and it again makes the code that much more readable. Now let's take a look at the synthesis of VHDL, how VHDL can be used to synthesize logic. Again, remember that RTL synthesis refers to the act of reading a snippet of VHDL code and translating it into hardware. So I code, for example, again, this case statement with the intent of building this MUX. The synthesis tool reads the HDL, translates it into gates. Once it's translated into gates, then the synthesis tool will do a second step and perform optimization of that logic to make it smaller, faster. To that end, when doing RTL synthesis, we do two basic types of process statements: the combinatorial process and the sequential process. With the combinatorial process, we have a process that includes all inputs in the sensitivity list. So any signal that is used on the right hand side of an assignment inside the process goes into the sensitivity list. This will generate a combinatorial block of logic. The other type of process is a sequential process. With a sequential process, we want to generate registers. So the sequential process is sensitive to a clock and any asynchronous control signals. It's important that you remember that these are the two different types of processes. If I'm building a process and I forget to leave off, if I leave off one of a combinatorial process and I leave off one of the signals from the sensitivity list, the synthesis tools will recognize that it's a combinatorial process, and they will actually assume that that signal should have been in your sensitivity list, and they will synthesize the logic based upon that. A simulation tool will simulate exactly what is written. So the behavior of the process in the simulator will not be the behavior of the process in the synthesis tool. So it's very important that you always stick to either you have a combinatorial process, all inputs in the sensitivity list, or you have a sequential process and you're building registers. The combinatorial process is pretty straightforward. Any signal that is on the right hand side of an assignment statement in the process needs to be in your sensitivity list. So we're going to take a little bit more look at sequential processes. Let's say, for example, you want to build a D flip-flop. The IEEE has defined a function called rising edge that allows us to check the clock looking for 0 to 1 transitions. So here we have our logic, and down in our process we have a process that is only sensitive to clock. So if the clock transitions, this process turns on and begins executing. The first line we see in the process is if rising edge clock. Again, that function says, has there been a rising edge on the clock, a 0 to 1 transition? If there has, then the D is allowed to, the Q is assigned the value of D. If the clock transitions, let's say it transitions from 1 to 0, then the rising edge text would fail and the Q output would not change. Along with the rising edge function, the IEEE has also defined a falling edge that you can use that indicates that a 1 to 0 transition must occur. Any other type of transition, including X to 1, Z to 1, H, L, none of those would cause this process or would satisfy this function. The rising edge and falling edge must be 0 to 1 or 1 to 0 transitions. These functions are included in the standard Logic 1164 package, so no other package needs to be declared. Because you're using standard logic, you already have access to them. As a note, I do want to point out that some designers, instead of using the rising edge function, will use the clock tick event and clock equals 1 phrase. What this says is that has there been a transition or event on the clock signal such that the result is 1, thus a rising edge clock. For a falling edge transition, you can say clock tick event and clock equals 0. While the rising edge function and the clock tick event and clock equal 1 will both synthesize to the same logic, a D flip-flop or register, they are different in simulation. Whereas the rising edge again does specify the transition must be 0 to 1 or 1 to 0, the clock tick event and clock equals 1 or 0 does not. So we do recommend you use rising edge and falling edge functions. In this example, we want to implement a D flip-flop again, but this time we want an asynchronous clear. I mentioned a couple slides ago that if you want to build a sequential process, then in the sensitivity list goes the clock and any asynchronous register control signals. So in this case, we have a process that is sensitive to the clock and the clear. The second requirement for doing an asynchronous control signal is that you must test for the control signals before you test for the rising edge or falling edge clock. So in this example, I check to see if the clear is 0. If the clear is 0, then the output is zeroed. Only if the clear is not been asserted do we check the rising edge or check the clock for a rising edge, and then if that occurs, we assign Q to D. Thus, we get an asynchronous behavior. If the clear gets asserted, the process turns on and clears out the Q. Regardless of what the clock is doing, as long as the clear is asserted, the Q stays clear. Only once the clear is deasserted and the clock does a rising edge, then do we satisfy the else if, and then Q is assigned a value of D. So the rules for doing asynchronous control signals is they must appear in the sensitivity list of the process, and we test for the asynchronous control signal outside of the else if that checks for the rising edge condition of the clock. Therefore, the clear equals 0 is not dependent upon the operation of the clock. Here's an example using a synchronous clear. With a synchronous clear, the opposite is true. We do not test for the clear. We do not test for an asynchronous signal in the process sensitivity list, and we nest the synchronous signal underneath the rising edge. So let's look at this example.